Welcome to Advanced Learning Tutoring. This is the Physics playlist. Please like this video and subscribe to our channel. Energy stores and systems. A system is an object or group of objects. There are changes in the way energy is stored when a system changes. Energy cannot be created or destroyed, only transferred from one store to another. Examples of the energy stores can be summarized by the mnemonic leg to neck. L for light energy, E for electrical energy, G gravitational potential energy, T thermal energy or heat energy, N nuclear energy, E elastic potential energy, C chemical energy, and K kinetic energy. Energy can be transferred from one store to another. For example, an object projected upwards, a moving object hitting an obstacle, an object accelerated by a constant force, a vehicle slowing down, or bringing water to a boil in an electric kettle. An example of a chemical energy store would be food or a battery. Energy can be transferred by one of the following ways: by doing mechanical work, where a force moves an object through a distance; by electrical work, where charges move due to a potential difference; by heating, due to temperature differences caused electrically or by a chemical reaction; or radiation, where energy is transferred as a wave, for example light and infrared. An example of a description of an energy transfer. Thinking about a remote-controlled car. The chemical energy store in the battery is converted to the kinetic energy store in the wheels using an electric current. Therefore, the chemical energy store is transferred to the kinetic energy store electrically or by an electrical current through the wires. Gravitational potential and kinetic energy. The amount of gravitational potential energy gained by an object raised above ground level can be calculated using the following equation. Gravitational potential energy equals mass times gravitational field strength times height. Height above the surface is measured in meters. This equation is not given on the physics equation sheet. The kinetic energy of a moving object can be calculated using the following equation. Kinetic energy equals a half times the mass of the object times the velocity squared. Mass of objects are measured in kilograms and the speed or velocity of the object in meters per second squared. Both of these equations are not given on the physics equation sheet, so must be learnt. Gravitational potential and kinetic energy exam question. The miners working in a salt mine use smooth wooden slides to move quickly from one level to another. The vertical drop is 15 meters. A miner of mass 90 kilograms travels down the slide. Calculate the change in the gravitational potential energy of the miner when he moves 15 meters vertically downwards. The gravitational field strength is 10 newtons per kilogram. To calculate gravitational potential energy, we multiply the mass by the gravitational field strength by the height. So that is 90 times 10 times 15, giving us a change in the gravitational potential energy of 13,500 joules. This is the amount of energy the miner has at the top of the slide. As soon as the miner moves and travels down the slide, we can assume that all of the gravitational potential energy is converted into the kinetic energy store, as energy is transferred from one store to another. This assumption is not 100% correct in true life. because energy is dissipated to the surroundings. So not 100% of the gravitational potential energy will be transferred to the kinetic energy store. To calculate the maximum possible speed that the miner could reach at the bottom of the slide, we use the kinetic energy equation. We have to recall that kinetic energy equals 1/2 times the mass times the velocity squared. We need to rearrange this equation to calculate the velocity. We assume that the kinetic energy is 13,500 joules. Divide this by 1/2 times the mass, and then we square root our answer to find the velocity of 17 meters per second. The speed of the miner at the bottom of the slide is much less than the calculated maximum possible speed. Explain why. Work is done against friction between the miner and the slide. Due to friction, kinetic energy could be transferred as heat energy to the surroundings, and therefore the kinetic energy will be lower and in turn will result in a lower value of the speed. Elastic potential energy. The amount of elastic potential energy stored in a stretched spring can be calculated using the equation elastic potential energy equals 0.5 times the spring constant times the extension squared. Elastic potential energy is measured in joules, spring constant is measured in newtons per metre, and the extension, referring to the increase or decrease in length, is measured in metres. Note here that springs can both be extended or stretched, but also compressed, for example springs in a mattress. So extension could also refer to the compression of a spring. A spring has a spring constant of 3 newtons per metre. It is stretched until it is extended by 50 centimetres. Calculate the elastic potential energy stored by the spring, assuming it is not stretched beyond the limit of proportionality. You are given this equation for elastic potential energy on the formula sheet. First is to convert centimetres to metres. 1 metre is equivalent to 100 centimetres, so 50 centimetres divided by 100 gives a length in metres of 0.5 metres. Elastic potential energy equals 1/2 times the spring constant times extension squared, so that is 1/2 times 3 times 0.5 squared, giving us an elastic potential energy of 0.375 joules. The limit of proportionality is the point in which the spring will no longer return to its original shape. Beyond this, the spring is said to be deformed. This happens when you stretch a spring so much it will not return to its original shape. Changes in energy systems. The amount of energy stored in or released from a system as its temperature changes can be calculated using the equation change in energy equals mass times specific heat capacity times the temperature change. The change in thermal energy is measured in joules, mass is measured in kilograms, and specific heat capacity is measured in either joules per kilogram degrees Celsius or kilojoules per kilogram degrees Celsius. Be careful to check your units in exam questions. If the units for specific heat capacity are in kilojoules per kilogram degrees Celsius, then the change in thermal energy will be in kilojoules. Specific heat capacity is defined as the energy required to change the temperature of 1 kilogram of substance by 1 degree Celsius. An example question. Sadie is experimenting with a model steam engine. Before the 0.25 kilograms of water begins to boil, it needs to be heated from 20 degrees up to 100 degrees Celsius. If the specific heat capacity of water is 4,180 joules per kilogram degree Celsius, how much thermal energy is needed to get the water up to boiling point? Just to note at this stage, if we were talking about the water boiling, then we would be looking at the specific latent heat of vaporization data. As we are just increasing the temperature of the water and not changing its state, we refer to the specific heat capacity equation. So the change in thermal energy is calculated by doing mass times specific heat capacity times temperature change. That's 0.25 kilograms times 4,180 joules per kilogram degree Celsius times a temperature change of 80 degrees Celsius, giving us a change in thermal energy of 83,600 joules. Changes in energy systems required practical. Investigation to determine the specific heat capacity of one or more materials. The investigation will involve linking the decrease of one energy store to the increase in temperature and subsequent increase in thermal energy stored. We will be using a joule meter, a power supply, a heater, material block that you will be investigating the specific heat capacity of, insulation and a thermometer. This is the method used. Place the immersion heater into the central hole at the top of the block. Place the thermometer into the smaller hole and put a couple of drops of oil into the hole to make sure the thermometer is surrounded by hot material, as air is a good insulator. Fully insulate the block by wrapping it loosely with cotton wool. Record the temperature of the block, connect the heater to the power supply and turn it off after 10 minutes. After 10 minutes, the temperature will still rise even though the heater has been turned off, and then it will begin to cool. Record the highest temperature that it reaches and calculate the temperature rise during this experiment. The block had a mass of 1 kilogram and the heater was running for 10 minutes. In physics, when we calculate with time, we convert the units from minutes to seconds. So 10 minutes is equivalent to 600 seconds. To calculate the energy transferred, we are using potential difference times current times time. The potential difference from the power supply was 10.9 volts. The current, 3.65 amps, recorded from an ammeter, times the time of 600 seconds. The energy transferred from the power supply was 23,700 joules. Rearranging the energy transfer and specific heat capacity equation, we rearrange this to get specific heat capacity equals energy transferred divided by mass times temperature change. So 23,700 joules divided by 1 kilogram times 23 degrees Celsius gives us a specific heat capacity of the material of 1,030 joules per kilogram degrees Celsius. Changes in energy, power. Power is defined as the rate in which energy is transferred or the rate in which work is done. Power equals energy transferred per second. Therefore, to calculate power, you're doing energy in joules divided by time in seconds, or work done in joules divided by time in seconds. These equations are not on the physics equation sheet. An example question: calculate the period of time in seconds during which 600 joules of energy is provided to a 30-watt light bulb. Rearranging the equation gives time equals work done divided by power. The units of power are watts. The time is 600 joules divided by 30 watts, equaling 20 seconds. The more powerful an object, i.e. the greater the power, the more energy is transferred per second. Conservation and dissipation of energy. Energy cannot be created or destroyed, only transferred, stored or dissipated. Dissipated means spread out. You must be able to describe with examples how in all system changes energy is dissipated so that it is stored in less useful ways. This is often described as being wasted. An example, a light bulb has 500 joules of electrical energy input. This is transferred to 400 joules of light energy. Therefore, 100 joules of energy is wasted and lost as heat to the surroundings, in the form of thermal energy. Explain ways of reducing unwanted energy transfers, for example through lubrication and the use of thermal insulation. Heat energy can be lost from a house through the roof or through the windows. Adding loft insulation or double glazing will help reduce energy loss to the surroundings as heat. The higher the thermal conductivity of a material, the higher the rate of energy transfer by conduction across the material. Thermal conductivity is a measure of how well a material conducts energy when it is heated. Metals, for example, will have a very high thermal conductivity, as they are good conductors of heat. Thermal insulators required practical. Investigate the effectiveness of different materials as thermal insulators and the factors that may affect the thermal insulation properties of a material. Method 1. Investigating the effectiveness of different thermal insulators. Place a small beaker into a larger beaker. Fill the small beaker with hot water from a kettle. Put a piece of cardboard over the beakers as a lid. The lid should have a hole suitable for a thermometer. Place a thermometer into the smaller beaker through the hole. Record the temperature of the water in the small beaker and start the stopwatch. Record the temperature of the water every 2 minutes for 20 minutes. Repeat, each time packing the space between the large beaker and the small beaker with a different insulating material. Plot a graph of temperature on the y-axis against time on the x-axis. Method 2. Investigating thermal insulation. Wrap a sheet of newspaper around a 100 milliliter beaker. Fill the beaker with hot water from a kettle. Put a piece of cardboard over the beaker as a lid. The lid should have a hole for a thermometer. Place a thermometer into the beaker through the hole. Record the temperature of the water in the beaker and start the stopwatch. Record the temperature of the water every 2 minutes for 20 minutes. Repeat, each time adding another layer of newspaper around the beaker until there are 10 layers of newspaper wrapped around the beaker. Plot a graph of temperature against time. Efficiency. Efficiency is defined as how useful an object is. Efficiency can be calculated as follows. The useful output energy transfer divided by the total input energy transfer, or the useful power output divided by the total input. These equations are not given on the physics equation sheet. An example question. A 30-watt light bulb uses 600 joules of electrical energy in a certain period of time. In that time, it produces 450 joules of light energy, and the rest of the energy is wasted. Calculate the efficiency of the light bulb. The useful power output, or the useful energy transfer output, is 450 joules. Divide this by the total input energy, which is 600, and we get 0.75. Multiply this answer by 100 to get your answer as a percentage, in this case 75%. You can increase the efficiency or make the object more useful by trying to reduce the wasted energy output. This might be done by lubrication or using a more efficient light bulb. National and global energy resources. The main energy resources available are using fossil fuels, which include coal, oil and natural gas, nuclear fuel, biofuel, wind, hydroelectricity, geothermal, the tides, the sun, and waves. Renewable energy resources are ones that can be or are being replenished as it is used. Wind, wave, hydroelectric, sun or solar, and geothermal energy are examples of renewable energy resources. Non-renewable energy resources are ones that cannot be replaced when in use. Non-renewable energy resources will one day run out. Examples include coal, oil, and natural gas. Energy resources are used for transport, electricity generation, and heating. Some energy resources are more reliable than others. For example, the use of solar power. Solar panels on roofs are not reliable. This is because the sun is not always present. The same goes for wind and wind turbines. It may not always be windy. Describing the environmental impact arising from the use of different energy resources looks at fossil fuels. When fossil fuels are burnt, they release carbon dioxide, which contributes to global warming.